All right, so typically the scientific method begins with what? Not always. Science can happen in different ways. Some people might come up with some hypothesis initially, but they'll have some prior knowledge of the system. It just doesn't come out of the blue. Or sometimes there's serendipitous observations, for example, penicillin. But that was more of some kind of observation. Normally what we do is we start off with observation. And when we take observations, we try to be as quantitative as possible. And when we try to be as quantitative as possible, that involves measurements. So we try to take measurements. And so when we do quantitative observations, then we want to take measurements and we want to be as accurate and as precise as possible. And so we want accurate measurements. What are accurate measurements? Can somebody tell me what accuracy refers to? Let me do something here. Okay, does somebody have a good definition for accurate or accuracy? We want to take an accurate measurement. No? All right. Well, let me just save this. Accuracy means you want something that is close to the true value. So let's say if something is 5 inches long, then an accurate measurement would be like, oh, you measured it at 5 inches long. An inaccurate measurement would be, let's say it was 4 inches rather than 5 inches. So you're off by an inch. And so the closer you are to the 5-inch mark, the more accurate you would be. But accuracy depends on a number of things. And so this is how close the measurement is to the true value. So accurate. How close to the true value the measurement is. So how wide do you think this screen is here? Six feet? 7 feet? 1 meter? How wide do you think that screen is? Well, you might take a guess. Maybe it's a 6-foot wide screen. And if the true value is 6 feet, then that was pretty accurate guess, right? Or you might say 7 feet, or what if you said 10 feet or 20 feet? If you said 20 feet, then would that be very accurate? And so what some people say is, okay, you want to hit the mark. And so the common thing that people show is like throwing darts at a dartboard. So if we have a dartboard here and you have the bullseye in the center, you're aiming for the center here, and you throw a dart and the dart hits the bullseye, then you would say that was pretty accurate. But if you're way off here, let's say this is another dart, it's supposed to be a dart, and it's way off, then that's fairly inaccurate here. And so we want some kind of accuracy, but it depends. What are you measuring this with? If you're measuring this with your eyeball, is your eyeball very accurate, would you say, in estimating distances? Like, could you tell me the length of this room with your eyeball? Is that pretty accurate tool? And so you probably want a tool that's a bit more accurate than that. See, so like your phone, you might grab your phone and there's the measurement app. Have you ever thought how accurate is that? You have the start point to end point. Do you think that's pretty accurate? Maybe it's pretty accurate. I don't know how accurate that is. It depends. It depends on, if you have like the phone app and you're measuring the distance, then it depends on how it was calibrated, if it was calibrated accurately or not. Or you go and you get a gallon of gasoline. Have you ever thought how accurate that is? Are you really getting a gallon? Are you getting less than a gallon or more than a gallon? What do you think? You know, and and then the temperature. Gasoline. A lot of liquids, what they do is they expand when the temperature goes up, and they contract when the temperature cools down. Not much, but a little bit. A little bit. As the temperature goes up, you got more kinetic energy, but the particles are still kind of stuck together. They're sticky, and so the volume expands. Well, on a hot day versus a cold day, are you getting the same amount of gasoline? And the volume is probably not the best way of measuring that, because a gallon of gas on a hot day is actually less than a gallon of gas on a cold day. Do you know that? Well, no, it's not, because a gallon is a gallon. You know what's less or more? It's the amount of gasoline you get. Really, if we want something that's accurate, then we probably shouldn't. Well, we could use volume, but we probably should use what? Like, if you're going to fill up an airplane and you know that the fuel expands or contracts, are you going to use volume? Well, you could use volume if you know something else. If you know something called the density. The density relates volume and mass. We're going to do a density measurement today. But it's a mass to volume ratio. And so on a hot day, it's a little bit less dense, and so you could figure out, really what we should determine is how many, what? Well, probably what we should do is we should determine how many kilograms of gasoline you have, because kilograms is a measurement of, well, weight is a little bit different, mass. And mass is directly proportional to the amount of matter that you have. And so then it wouldn't matter, if a kilogram of gasoline is a kilogram of gasoline. It doesn't matter if it expands or contracts. And so if you're going to fill up an airplane, you probably want to fill it up by mass rather than by volume, because the volume can change a little bit, right? And so when we take measurements, we want to be as accurate as possible. We want to know exactly how much matter there is, for example, fuel, because is it going to be enough to make it to the destination and then some? There have been cases where planes have actually run out of fuel due to some measurement errors. But okay, so how close the true value? Sometimes you can guess, and you can guess inaccurate. But is guessing going to always be accurate? No, that was like random chance. Random chance you might have gotten it accurately. So I'm going to guess the length of this. The length of this I'm going to guess as 6.25 meters. If I guess that as 6.25 meters, then it might be accurate. It might not be. But there's one other component to measurement that we have to worry about, and that is, in addition to accuracy, we want precise measurements. So we want accurate measurements, and we want precise measurements. Now, one thing is this. When we're dealing with accurate measurements, we have to make sure that the instrument is calibrated. And so one of the most important things here is calibration. Calibration is just simply making sure that the reading is correct. And this is like if you go to the supermarket, you look at the supermarket scales, they have a little calibration mark on the cash register because they're charging you for weight. Weight is a little different than mass. Does somebody know the difference between weight and mass? Uh huh. Yeah, yeah. Weight depends on gravity. So if you're in an elevator, and the elevator is going up, do you know if you're standing on a scale, you would weigh more? And then if you're on an elevator and the elevator is going down, do you know you'd weigh less? Or if you go to the moon, or if you're out in space, then you'd weigh on the moon you'd weigh 1/6 because on the moon they have 1/6 the gravity. In space you could be actually weightless in space. So you stand on a scale, it's not going to register anything. And so weight changes. Just we want something that doesn't change. And what doesn't change is mass. Mass doesn't change. And so if you want to know how much gasoline you purchased and you're getting the correct amount, then you want to know how much mass, how many kilograms. Weight is usually in pounds. Mass is normally in kilograms, and mass is the quantity of matter. And the quantity of matter doesn't depend on gravity. And so 1 kilogram in the elevator, whether it's going up or down, is not going to change. 1 kilogram on Earth is going to be the same as 1 kilogram on the moon because we don't lose any atoms or molecules or formula units there. Uh-huh. Yes. Do we have a way of measuring kilograms? We do. We use the same thing. We use a scale, and the scale's just been calibrated to read the correct number of kilograms. Now, if you took that scale and brought it to the moon, then it would be improperly calibrated. We'd have to recalibrate that scale so it's still reading the number of kilograms because the scale is going to be work. This is the way the scale works: is we need gravity to ensure that it's operating properly, and so that's the calibration part. For us, though, physicists wouldn't use these interchangeably, but chemists often do because chemists work in a laboratory, and the laboratory is not in an elevator that's moving up or down. The force of gravity on Earth is fairly constant, 9.8 meters per second, and so we use these interchangeably. Uh-huh. No, it changes so little that don't worry about it. Even though these aren't the same, for chemists, we use the word weight to mean mass. So when we say go weigh something, we just mean measure its mass. Since the force of gravity is fairly constant on Earth, on Earth, then we can come up with this equivalency. And it depends on how you want to express it. There are 2.202 pounds, or sorry, not pounds, kilograms, 2.202 kilograms per pound. So 1 pound is about 2 kilograms. Oops, did I get that right? I think I got this backwards. I got it backwards because a pound is a bigger unit. No, kilogram is a bigger unit. So I have this backwards. I had it right the first time. So let me correct that. When we take measurements, if you make an error in your lab notebook, you usually just cross it out like this. So if I made an error, you don't want to do this. This is considered poor technique. We make errors. The lab notebook, the book with a sewn binding, you don't have to keep that neat. People make errors all the time, and so this is the proper way. If I made an error, you just cross it out with a line or two, and then we can write the correction. It's 2.202 pounds per kilogram. Or whichever one's easier to memorize, 453.6 grams per pound. I usually just remember one. Is useful. But this is not on the official memorization list. If you forget this one, it's okay. And so we could relate weight and mass as long as the gravity is constant. If gravity is constant, then this is correct. If the gravity changes, then this is no longer correct. But since we're not going out in space, we're not going to the moon, we're just staying in the lab, the gravity is not changing, therefore this relationship is not changing. So people want to know, the gasoline pumps are calibrated. Are the gasoline pumps calibrated by volume or by mass? The gasoline pumps are calibrated by volume. And I always wonder, what is the temperature? How much does the temperature fluctuate? The tank for the gasoline is underground, so maybe the temperature doesn't fluctuate much. But if the temperature does fluctuate considerably, then you might not be getting as much gasoline on a hot day as you would on a cold day. Not that it makes much difference, but with the price of gasoline now, it's significant, could be quite significant. And so calibration, we need to make sure the instrument is properly calibrated, and therefore we can know that it's making accurate measurements. And so you got to calibrate your arm with your eye so you can hit this bullseye in the dot. But that calibration is very difficult, and so I couldn't do it. But for scientific instruments, we should be able to do it without too much trouble. So the way they do it for balances is they have what are called standard masses. And so, for example, a standard mass can be used. And so if we have something that we know weighs, let's say, 1 kilogram, in fact, usually standard masses, we try to be what we call as precise as possible. We don't say 1 kilogram in science. We would say 1.000, kilograms. This would be an example of a standard mass. If we know that this object weighs 1.000 kilograms, we put it on the scale. Scale we call also balance. It used to be balance beams. In fact, we have some balance beams, I think, here. And so that term carries over. Scale or balance. And we got to make sure it's reading that. If it's reading that, then it's properly calibrated. We also look for precision, too. So what do we mean by precise? What we mean by precise is something that's reproducible. So if I eyeball lengths, like, okay, the length of this screen, the height of this locker cabinet, the width of the door, the length of this room, and I use my eyeball, is my eyeball very precise? Would you say? No, nor is it very accurate, I think. And so what precision is how reproducible that measurement is. There are two ways that people usually think about precision. The first way is this. Like, for example, the scale. If I had a meter stick with no markings, it's just 1 meter, and then I measured an object. Let's say I measured this object's length here. I wouldn't necessarily call this very precise because I can't narrow the range. And so one way we think of precision is by how narrow this particular range can be. So this would be a low precision ruler, let's say, or meter stick. Versus if I had a meter stick that had markings here, and then I measure the same object, then this would be high precision or higher precision. Now, what I mean by this is this. Right now, I can narrow it between two markings, this marking here and this one here. And then I have to guess here. This is my guess, where this lies in relation to these. I don't have to guess. So this is not a guess. In other words, I know this, and I know this. And so I know it's between the beginning and the end of this, and that's 1 meter. And then I guess where it is in relation to the beginning and the end of this. That's a pretty wide range. Whereas if I have this meter stick, let's say this meter stick were marked at every 1 millimeter. So if I take a look at this, then I know this, and I know this mark, what the measurement is. As long as it's properly calibrated, I know those marks are accurate. But I'd have to guess here. And when I guess here, that gives me a much narrower range. And so let's give you a more concrete example. What would you guess that the length of this green thing is here? Let's take a guess. Uh-huh.
Maybe like half a meter.
Like a half a meter? Would you? Well, you know what? I would guess that it's a little bit past a half.
0.5?
Hmm?
0.5?
Point what?
5.
2.5? 0.55? I think, yeah, you could guess that. For sure, we see it's greater than half, maybe. Maybe we shouldn't be that precise. Maybe we should just go with, I'm just going to guess it's like 0.6 meters. That's my guess here. And this is my, what we call estimated digit. I'm estimating this one. So let's say we know this one, and let's say this one we're 0.61. Let me go with, we're going to go with millimeters here, 0.613 meters. And then I know this one here, this is going to be 0.614 meters. And so I'm going to say that this is in between 0.613 and 0.614. And so where would you guess that one is? Before halfway or after halfway or what? So what I know is it's greater than 0.613. Is there any uncertainty that it's more than 0.613? And so these are what we call certain digits. But I'm going to guess that it's more than 0.613. How much more than 0.613? If it's right in the middle, we call it 0.6135. Would you say it's right in the middle or maybe a little bit before? At least where the arrow is, a little bit before. And so maybe we'll just guess it at 0.6133, maybe 3/10 of the way. What do you think? So this is my guess or estimated digit, 0.6133 meters. Does that make sense how I guess that?
Yeah.
When I guess it, I try to divide the space here. And so if I know that this is 0.613 and this is 0.614, then I try to divide the space. So right in the middle, I'm going to call that 0.6135. And then I'll go 1, 2, 3, 4. So the first line here would be 0.6131, 0.6132, 0.6133, and then 0.6134, and then finally hit 0.6135, and then 0.6136, 7, 8, 9, and then 10. The 10th place would be 0.614. And so what I do is I try to visualize these lines in my imagination. And so I'll try to visualize They aren't printed and then guess. Which one of those lines lines up with the green object here? And so I'm just guessing the third one does. So that's my guess there. So do you see how much narrower the range is? What we usually do is something like this. When we have two measurements like this, are those two the same or different? Well, they're the same in that they're both 0.5, but what's different is their precision. Because of the way we guess things, like I just showed you up here, when I have 0.5, I think of a range. And I think of the range as being like, say, plus or minus, half the unit, the smallest unit, which would be 0.1 here. And so I would say like plus or minus about 0.05 meters. So this one can range from 0.5, let's say 0.54 to about 0.45 meters. Whereas something like this is much more precise. It's going to have a much narrower range. So if we do this, we see that this is going to be what we call the estimated digit. The last digit is always estimated, and we're only allowed one. And so the 5 here. Whereas over here, this is going to be the estimated digit. We're estimating that it's laying right on that line. Estimated digit here. And so that narrows the range quite a bit. And so this is going to be plus or minus 0.0005 meters. And that means the expected range for this would be something like, I'm going to drop it down from 5 to 4. But this could be anywhere from 0.5004 to about 4,995 meters. And so we see a difference in the precision. This measurement has much higher precision. And therefore, we say that this one is a low precision ruler, this is a high precision ruler. And normally, the more precise, the higher the precision, the more expensive it is. So if you have high precision instruments, that's good. But high precision doesn't mean it's accurate. What do we have to do to make sure it's accurate? What do we call that testing procedure? No. That is a very specific name. Calibration. We got to make sure it's calibrated. If it's not properly calibrated, even you could buy the most expensive, the highest precision instrument, but if it's improperly calibrated, it's not going to give you accurate readings. Uh-huh. I'm sorry? Yeah. Higher precision usually means higher accuracy, but not always. It's got to be calibrated. And so when we think of measurements, we want accurate measurements. Is it properly calibrated? And we want precise measurements. Precise means we can pinpoint it. And so let's say somebody asks you, they ask you to pick me up, come pick me up. And they give you a very imprecise coordinates, then you could be looking for them for a long time. Pick me up. I'm in Torrance. Well, that's not very precise, you know. Or pick me up. I'm here at the chemistry building at El Camino. That's much more precise. And so we want higher precision. And these are looked at separately. Precision and accuracy are looked at separately. Okay. So let's take a look at today's lab. Normally, when we before lab, you should read the experiment, so you have an idea of what's happening. What you want to do is you want to have some kind of mental picture of what's going on. But sometimes you can't really generate mental pictures because you don't know the instrument or you don't know the technique or those types of things. And so things that are confusing, you want to ask, you know, at the beginning of the lab, unless they're discussed in the lab discussion. But at certain places, like at UCLA, most of the labs have a pre-lab quiz. And so, like when I was a student there, every single lab, you go in and immediately you get hit with a quiz. And the quiz will cover something in the discussion to see how well you understood and comprehended the discussion. And so before lab, we try to generate this mental picture of what's going on and then conceptually understand it and get that cleared up before coming into lab so that you're prepared for the pre-lab quiz. That was at UCLA. A lot of schools will have pre-lab quizzes. I don't have pre-lab quizzes. And then notebook prep. And so, as I said, some of you didn't have the notebook before, but you want to reserve the first 1 or 2 pages for a table of contents. And so you can just leave this blank for now. And then we number the pages, you know. And so you could start the table of contents with a number or not, but page 1 was, or this might be page 1 or page I maybe. This was the lab burner. If you didn't do the lab burner in this, then what you could do is you could just staple, you know, or tape. Your notes here for the lab burner. And so sometimes that happens. You forget your lab notebook. Just do it on notebook paper and make sure you insert it into your normal lab notebook. Maybe 2 pages. We still aren't completely finished with this, so brings us to page 3 for the measurements. Now, when you go on in science, the labs get progressively harder and harder. What happens is, everybody starts off at the same time, but they quickly separate. You'll have the people that are pretty fast and the people who are pretty slow. And is there enough time? Well, at UCLA, there's usually not enough time. So the really slow people don't finish. They get left behind, unfortunately. And so that means they got to get faster and faster. There's a certain minimum speed you have to go. And so if I like to take my time, so I don't like to rush, If you like to take your time, you don't like to rush, then you should prepare more before lab to make it go faster. And so there's certain things you could do to prepare more, And so in typical lab, that is going to be difficult to get done. We start off with a title and then like a short objective, or description. And then what I like to do is I like to divide this page into two things. Over here, I like to write out the procedure. But I don't like to just copy the procedure from the lab manual. It's normally there. What I like to do is I just like to either have a brief, condensed, procedure, or like drawings. I like to do it by drawings. So let's take a look at our lab here. And so this lab begins with a title and some objectives. Those you can paraphrase. We don't need the discussion in there. You could read the discussion. And then we have a density of water. And then we come up with a procedure. This one's pretty self-explanatory, so there's not much here to do. And so I look at this. I need the mass of an empty graduated cylinder. I need the mass of a grad cylinder and 15 milliliters of water and 30 milliliters and then 45 milliliters of water. And then I need to measure the temperature. I need to measure the volume of water here. Okay. And so in this particular case, let me see what else they have written down here. Oh, here's the procedure here. So procedure part A here. There are 5 independent parts of the experiment. Part A through E can be completed in any order. In parts requiring electronic balances, you should use the same balance throughout that part. When recording masses from electronic balance, all digits should be reported. And so A, density of liquid. You'll determine the mass and volume of 3 samples of water and calculate the density of the water. Weigh a dry 50 milliliter graduated cylinder on an electronic balance. So we'll have to check in, then try to do this. So let me see. A graduated cylinder, if you want to look, there's an equipment sheet near the end of this or at the beginning of this. Let me see. Maybe it's gone. This is what a graduated cylinder looks like here. And so this is the way I'd write the procedure. I'd read through the procedure and then just try to draw it out pictorially. And so let me show you what I mean by that here. Milliliter is spelled a little m, big L, and that's just the volume. So the total volume for this can be measured up to 50 milliliters. We can measure volumes up to there. And so dry 50 milliliter, and then I just have mass blank. Now, your lab notebook, it doesn't matter if it's dirty or messy or you have a bunch of errors in there. It doesn't matter because you're not graded based on how neat your lab notebook is. But if you're submitting a formal report, do you want a whole bunch of mistakes in the formal report, a bunch of errors, a bunch of corrections? Do you want to submit that as your final formal report? No. And so this is the reason why we have a lab notebook. We have a lab notebook to keep your report sheets clean. Not only that, if you give a report to somebody, you say, okay, here's my final report. Okay, when am I going to get it back? Usually when you give reports, you don't get them back. You give a report, they keep them. Except, your students here. But in normal science, you make extra copies. So you always have it. Well, that's something you could do is you can make a copy of the report. Or what we do is we just keep all our raw data. All our raw data goes into the notebook. So if we need to generate new reports, we can easily do it because we have all the data. But let's say you gave your report to somebody and that somebody lost your report. And you go, oh no, that contained all my data. And the only way you can regenerate a report is to redo the experiment. Do you want to redo the experiment to regenerate a report? No. And so we need a permanent copy of the data because with the data, then we can always write a report. And so this is why we have the lab notebook. We have the lab notebook to keep your report sheets clean. What is your report sheet? Well, your report sheet is this. Now, it's quite convenient because the report sheet has, tables, and you can write your data in these tables here, like this. But this is what you're turning in to get graded. And so the best is just to leave this blank and then write all the data in your notebook. And so what you could do is you could just write this table into your notebook, but some of the procedure is missing. And so when I look at the procedure, let's go ahead and read the procedure here from that data table. Some of the procedures missing. So weigh a dry 50 milliliter graduated cylinder on an electronic balance. Remove the cylinder from the balance and add about 15 milliliters of water using a plastic squirt bottle. The volume doesn't have to be exactly 15 milliliters. Measure and record the volume and new mass on the report sheet. Subtract the mass of the empty cylinder from the mass of the cylinder plus the water to determine the mass of the water. Repeat the volume and mass determinations for about 30 milliliters and 45 milliliters. Measure and record the temperature of the last sample of water. Using the table on page 4, determine the accepted density of water at your experimental temperature. Using your average density of water, determine your percent error. If your absolute percent error is greater than 3%, repeat the trial that is furthest from the accepted value. So what I do is I don't want to write that verbatim. I just want to kind of summarize that using little pictures or something like that. And so I do dry 50 milliliter, and then I do plus, it said 15 milliliters. And it says it didn't have to be exact, so I'm going to use tilde here. So about 15 milliliters of H2O in a squirt bottle. Now, we have squirt bottles here. And they're located in these white baskets. Do you see those here on the counter? Okay, now what we need to do is we need to measure the mass and the volume as precisely as possible. So even though, you know, what they mean by it doesn't have to be exactly 15 is just get it about 15 and then measure it as precisely and as accurately as possible. So about 15 milliliters of water, but we want as precise and as accurate of mass and volume measurements as possible. And then this gets a little confusing. What we're going to do is we're going to do another about 15 milliliters of water. So the total volume is around 30 milliliters. And then we want to measure the mass and the volume as accurately as possible. So this is the 30 milliliter. And then we're going to do another plus 15 milliliters. So now the total volume is going to be about 45 milliliters. Not exactly, but approximately 45 milliliters. And then we're going to measure the mass and the volume as precisely as possible. And then we're going to get a thermometer and measure the temperature of the water. The thermometers are located on that white rack in between these two green, what are called hoods. And they're standing there. Try not to break it. I don't think those are mercury. I think those are alcohol thermometers. You know, alcohol is another liquid that expands and contracts with temperature, like gasoline, you know. And you can watch it expand and contract with temperature, and that's going to, as long as it's properly calibrated, that's going to tell you what the temperature of this liquid is. And so we're going to measure the temperature of the water, which we call T, as precisely and accurately as possible. All our measurements are going to be with the maximum precision that we're allowed. Okay, then we're going to do some calculations. The calculations can come at the end here. Try it. So we'll just do this one run through here and then we'll try it again. Or we could just do the first part and then check our calculation. Maybe we should do that. But the situation is, how many times are we doing this? So we're doing this we're measuring the mass here. And do you see this little asterisk here? That little asterisk means calculation. This asterisk means calculation here. And so for the raw data, our measurements, we have total mass and volume and temperature. The rest are calculations. So let's take a look at measuring volume first, and then we'll look at measuring mass. Actually, so we need about 15. It doesn't really matter, you know, how much. This is a 50 milliliter graduated cylinder, goes up to 50. We're going to be using the right side scale here because we're starting here at 0 and then filling this up. And so we're going to get it close to 15. And when I fill this with water, it's going to look like this, something like this. the surface of the water is curved like this, and the reason it's curved is because water loves sticking to glass. Water likes sticking to glass more than other water molecules, so it prefers to be with glass than with other water molecules, but it can't climb too high because of gravity. Eventually it'll try to stick as much as possible to the glass, and then gravity is going to prevent it from going up higher. Now, if this tube were really small, then it's less of a factor because you don't have to fight gravity as much. And so we have something called capillary action, in which water can climb up really thin tubes quite high. But a big tube like this, it can't climb very high. And so what we do is we take a measurement. Now, when we take a measurement, we want accurate measurements, but the accuracy comes from calibration. Was this properly calibrated? So at the 15 mark, this is the 15 mark here. At the 15 mark here, is it really 15 milliliters? That would be accuracy. Well, we don't know. But the other thing we were going to do is we're going to try for precision. Okay, the next marking here is 16. We call this 16.0 milliliters. It's right on there. And this is going to be 17.0, then followed by 18.0, 19.0, and 20.0. The 0.0 just means it's right on the line. Now, take a look at the volume. Now, where do we measure the volume? Do we measure it by how high it climbs? No, we measure it from the bottom, the valley here. And when we measure it, we got to make sure we get consistent measurements, because another way we think about precision is by reproducibility. Two ways. The narrow range, and I didn't get to the second way. The second way here is reproducibility. And so the second way of thinking about it is how reproducible. You might hit the bullseye one time, but can you consistently hit it? So if somebody threw 3 darts and those 3 darts landed on the bullseye, then you would say high accuracy, and high precision. But let's say somebody threw 3 darts and all 3 darts landed in the same spot, but they're off. They're aiming for the bullseye, which is here in the center, but they hit over here on the right. What would you say about these 3 throws?
Low accuracy.
Yeah, low accuracy, high precision. And then something like this could be corrected. There's some kind of what we call systematic error here, and that could correct it. But what if the first dart landed bullseye, but they tried to go for 2 bullseye and they ended up throwing it off here, and then the third dart ended up being out here? What would you call this?
Low accuracy, low precision.
Okay, I'd for sure say low precision. But is it low accuracy? One of them was pretty accurate. And if you look at if you average the 3, the average is decently accurate, right? But overall, it's not. And so we look at accuracy. This is going to be a little bit trickier because here, this one was accurate, but the other 2 weren't. And then the average might happen to be accurate. Where's the average? The average would be around here. Which is somewhat accurate. What if the average is right in the middle? Then which one would be the best? Would you say A, B, or C? We want both. So we want both accuracy and precision. So even if the average was right in the center, bullseye, we still prefer A because it has both high accuracy and high precision. All right, so let's go back to what we're talking about here. I wasn't very accurate. It just said about 15, but it doesn't matter. I just get anywhere close to 15, so I overshot it. No big deal. What I want to do, though, is I want to take an accurate and as precise of a measurement as possible, but we don't know the accuracy of this, so I'm just going to try to take as precise of a measurement as possible. When I take a precise measurement, I want to make sure my eye is level with what we call the meniscus. And I'm going to measure it from the bottom here. Let's see. Oh, okay, that didn't quite work. Okay. All right, so I'm going to measure it from here. I want to measure it at the bottom of the meniscus or the valley. And so, should I have my eye level here? I shouldn't go red. Let me go. If I'm looking at it here, am I going to get a accurate measurement? No, I'm not. It's going to, this is close to maybe 16, 17, but this is going to look like it's 18, isn't it? And the same thing here. I don't want to measure it looking up at it. If I'm looking up at it, it's going to look more like 15, right? And so what I need to do is I need to make sure that my eye is perpendicular to the meniscus. In other words, I need to make sure I'm at eye level. It's supposed to be horizontal, but it's going to go horizontal for me. I guess not. So I need to make sure my eye is level. This is called parallax error. Parallax error is going to give you inaccurate. So if you're reading up high, then you're always reading a bigger volume. If you're reading down low, you're always reading a smaller volume. And so those are going to give you inaccurate measurements for sure. So first thing is we got to make sure we're reading eye level. Okay, then we want as precise of a measurement as possible. So how precise can we get? Okay, are we above 16.0? Yes. Are we below 17.0? Yes. So we could call it 16.0, but we could even be more precise than that. What would you guess? How far are we from 16 to 17? Are we halfway there? Or a little less than halfway? What would you say? 16.4? Okay, so what I do is I divide this up into smaller subdivisions, and I do this by drawing a line mentally in the middle, and then I'll go 4, 3, 2, 1, 0, 6, 7, 8, 9, 10. And so this would be my 15.0 mark here, or no, 16.0. This would be my 17.0. And then I have these lines, which I made in my mind, 16.1, up to 16.5, up to 16.7, etc. And so all these are my guess. They aren't marked there, but we're allowed one guess. And so we're going to guess that this is like 16.4. So we guess that this is 16.4 milliliters. Okay, that's fine. I'll use that 16.4 milliliters as my volume. Okay, what's the other data I need to collect? Okay, so let's go back here. And I need to weigh that. And so the volume I'll write here is 16.4 milliliters. And then I need to weigh it. First, before I even do this, I need to weigh it dry. And so I should have talked about mass first, actually, but let's go ahead and take a look at our balance. Balance massage. Balance mass. So we have different balances. We have the little less expensive balances. Our balances are not the most precise balances. If we look at the precision of this balance, it's 0.01. So it measures to the nearest 0.01 grams here. And our balances are the same. Our balances look like this. There's going to be a 0 button or a tare button. So with nothing on here, it should be reading 0.00 grams. So we zero it. If we were to calibrate it, we put a 1 kilogram standard mass here, make sure it's reading 1. If it's not, then we adjust the calibration. These have already been calibrated, or should have. And so what you'll do is you'll just put your empty grad cylinder on here and then record it to the nearest 1/1000th of a gram. Each person's grad cylinder is going to weigh a different amount, and they aren't all the same. And so let's say mine weighed, I don't know, 30.31 grams. So I put that in here. I want to be as precise as possible, so I'm going to write all the digits. Okay, now with the water, let's say it weighed 47.01 grams here. And then I have my first set of data. And so what I'm going to do here is I'm just going to add another 15 milliliters of water and weigh and measure its volume. And then add another 15 milliliters of water. So now I have about 45 milliliters, weigh and measure its volume. And then measure its temperature. Any questions on this so far? Uh-huh.
We're seeing procedure A right now, right?
I'm sorry?
We're just doing procedure A right now.
Yeah, this is just procedure A. So what we'll need to do is we'll need to check into the lab. This is procedure A. But we're going to talk about the calculations for procedure A here. And so let's take a look at that next. So we get the temperature of the water. Now for the calculations, we need a calculation of the mass of the water. Let's start calculation here. And so the mass of the water is going to equal the mass of the cylinder plus the water minus the mass of the cylinder. That'll give you the mass of the water. So this first calculation here is just taking this mass and subtracting out the mass of the cylinder. And then over here, the mass of the water here, now we have about 30 milliliters. So we'll take the total mass, subtract it from the mass of the cylinder, that gives us this, etc. Then we have the volume. Now the density of water is the mass divided by the volume. So we'll just take the mass here of water divided by the volume of water, and we get this calculation. And we get 3 values of that. And so these 3 values should be about the same. If they're way off, then we want to maybe double check this or redo it. There's another way we're going to check it. And so what we're doing is we're determining the density of a liquid, and this liquid's water. And we're determining the density by measuring its mass, measuring its volume, taking the mass divided by the volume, that gives us the density. Now the density of water changes with temperature because water expands and contracts a little bit with temperature. And so some people have measured it. It's a very small change. And so, for example, here, when we look at the density of water in this chart, this is the density of water from 15.0 to 15.1. So if we go from 15.0, it's 0.99909. And then we go to 15.1, what happened to the density? It went down a little bit. But did it go down by much? Barely any. And so what happens is that you can see as the temperature increases, what's happening with the density? It's going down a little bit. Do you see that? And the water expands. It expands a tiny amount, not much, a tiny amount. Gasoline expands a lot more. Water's a lot more sticky, so it expands less. But eventually from 15.0, we can go all the way to 30.9 in our table. At 30.9, now it's 0.99537. It used to be 0.99909, so you can see the water is a little less dense here. So if you have a gallon of water at 15.0 versus a gallon of water at 30.9, a gallon of water at 15.0 weighs more or weighs less? Weighs more. And so the same thing, a gallon of gasoline at 15.0 versus a gallon of gasoline at 30.9. Gonna weigh more of that. All right, so let me see what we're gonna do next. What we're gonna do, okay, when you're ready to start the experiment, you're gonna weigh the dry 50 milliliter dry cylinder and record the mass. You should have 4 digits, 2.2. Now we need a squirt bottle. The squirt bottle, we have 2 types of water that we could fill the squirt bottle with. We have tap water and we have deionized water. The deionized water has this white cap here. It's marked DI for deionized water. DW is distilled water. We don't have any distilled water. We just have deionized water. We'll talk about the difference later. But your squirt bottles should be filled with deionized water. If somebody accidentally filled it with tap water, we want to dump it out. So when you grab your squirt bottle, unscrew it, dump out the water in there, give it a little rinse with deionized water, and then fill it with deionized water. You don't need that much, but like halfway. And then we're going to use that for our measurement. So again, we have 2 types of water, tap water and deionized water. Tap water is good for the rinses. Deionized water is good for our experiments. Our final rinse should be with deionized water also. So we're going to make sure our squirt bottle has deionized water. So we'll put some fresh deionized water in our squirt bottle. I forgot to resume the video. All right, so these are all acceptable. It depends on what thermometer you have and where you measured it. These are mass-produced thermometers. They don't calibrate each one. If you buy a high-precision thermometer, then those are going to be calibrated, or you can calibrate those. So I'm just going to pick one set of data. We'll just go with this: 103.56 and 118.40 grams. I'll talk about it. Yeah.
Did it at the end?
No, we'll do it now. Yeah. So what did you get for the mass of the water on yours? Do you have a question?
Yeah. For volume, do I do this?
No, you measure it. You got to measure it.
So it's different for everything?
Yes. So just redo it. You got to measure it. What was the volume of water that you got?
14.74 grams.
15.3 milliliters.
Yeah,
What was the mass of water you got? 14.84 grams. So I'm just going to pick student A here. What was the temperature of the water you got? 21 point what? 21.2? So what I'm looking for, question.
I'm having trouble opening the lockbox.
Don't worry about the lockdown. Just worry about the experiment. Get started with the experiment. Yeah, the lock, don't worry about it. We can deal with the lock later. We just want to get started with the experiment now. Oh, yeah. Go ahead and record the combo, and then
I can take the paper.
take the paper. Don't forget to write the combo.
I'll take the picture.
Volumes. I want to make sure people are recording the volumes correctly. What did you get for, 15? What? Point what? 14.7? Okay. Any others? 14.95 is not good. The markings are 14, 15. So it's between 14 and 15. You can't guess 9.5. You can only guess one. So 14.95 is not correct. Okay, somebody else give me their volume. 15.9 is fine. Any other volumes? All right, let's go ahead with one set of data. So what I'm looking for is you're recording all the numbers off the balance, including the zeros. The zeros are significant. It makes it more precise. So 118.4 versus 118.40. 118.40 is more precise. We want to make sure we're recording all the digits. And then on the volume, it's about 15, but we want to know what it is as accurately and precisely as possible. So if it's about 15, you might have gotten over, you might have gotten under, but whatever. If you're over or under, it doesn't matter. We just need to know how much it is. And so here we're guessing one digit because the grad cylinder is marked at every milliliter, so 15, 16. So the 0.3 is just an estimate. 0.7 is an estimate. 0.9 is an estimate. Okay, so then we do a calculation. So we do this one. Let's figure out the mass of the water. Mass of the water is going to be the mass of the grad cylinder plus the water, 118.40, minus the mass of the grad cylinder, 103.56. And that gave you 14.84 grams, correct? And you had 15.3 milliliters, correct? All right, next we're going to calculate the density. All right, so when we calculate the density, again, this is going to be an asterisk here. So this is going to be the density of water. So I'll call D subscript water. And the density of water is just going to be the mass divided by the volume of water. And so the mass of the water is 14.84 grams. The volume of the water that you got is 15.3 milliliters. And so go ahead and punch that out in the calculator, and let's see what we get for the density here. So 1484 divided by 15.3. Okay, so this density comes out to 0.941. Okay, and I'm going to talk about this later, but we have something called sig figs that we got to deal with. And so I'm going to write all the digits in the calculator. 0.94117,647. But we're only allowed this. Here. The units of the density are going to be grams per milliliter. This is what we call the experimental density. What did you get? 9699. Okay. So wait, 0.96993. All right, let me do that. Correction. Let me fix this. I have a screen protector on my phone. Yeah. 0.96993,464. No, well, I'm going to carry extra digits here.
Sorry, back to the phone from last week, but I missed one for volume. Is that subtracting the mass from the total?
No, the volume you record directly from the grad cylinder. You just read whatever the reading is on the grad cylinder. There's no calculation for the volume. Yeah, but let me, we're going to do something else right now. You can just keep going. You can keep going and then collect the rest of the data, and then I'm going to come back to this calculation. I don't want you to round it yet.
So we just give you the exact value?
Just write down all the digits.
Okay.
And so I go here to 21, and then I go to 0.2 over here. So at 21.2, the theoretical density is 0.99794. Does everybody see how to use this table? Yeah? So if you have a different temperature, just look up the density at that temperature. So this was 21.2, so 0.99794. From table. Now what we're going to see is we're going to see that our experimental density and our theoretical density are off a little bit. Do you see that? And so what we're going to do is we're going to calculate the percent error. The percent error is equal to the experimental minus the theoretical divided by the theoretical times 100%. And so the experimental here is 0.969. I'm going to carry extra digits here, 93464, minus the theoretical, which is going to be 0.99794, divided by the theoretical, which is 0.99794 times 100%. And so let's go ahead and calculate this. This is going to be 0.9699464 minus 0.99794 equals divided by 0.99794 equals times 100. And so what I do is I do this in two steps. So the first step I'm going to do is this. Actually, this comes out to minus 2.806, 2.806311701. But the two steps I'm going to do is, first I'm going to do the subtraction. I forgot to do that. 0.969, 93464 minus 0.99794. So in the numerator of this, I get minus 0.029 46536 divided by 0.99794 times 100%. Okay, so this comes out to minus 2.8% error. That means I'm reading this 2.8% too small. If I were to stop here, then this would be it, but this particular one. Now, what did the experiment say? It said if it were more than 3%, redo it. What did it say in the procedure? 3%? So we're okay because this is less than 3%. Greater than 3%, we should redo. Less than 3%, it's okay. Huh? No, I mean plus or minus 3%. Uh-huh. All right. I'll talk more about the rules later. All right, and then what we're going to do is we're going to redo it. It doesn't ask you to calculate the percent error for each one, but we're going to calculate the percent error for each one. All right. And so that's going to be one difference. Determine the volume of water with the metal in there.